My goal was to measure the thickness of tissue layers, and we extended that to measuring retinal thickness. What I realized from the data was that I wasn't only just seeing from the front and back surfaces of the retina, but the instrument has such high sensitivity, 100 dB or 1 in 10 billion sensitivity, that we could actually see internal structures inside the retina. And that's what gave me the idea that this could be turned into an imaging modality.
So you're widely known for the OCT, which is optical coherence tomography. And could you explain to the listeners what is it and where they may have encountered more than, let's say, the visits of the ophthalmologist?
Well, I would define OCT as imaging with a interferometer using short coherence length light, so that you can measure the round trip time of light scattered back from a sample or biological specimen with very high depth resolution, generally on a micrometer scale.
So where can it be seen? So I mentioned that it's usually used like for retina analysis. And how it was like, let's say before, how was the retina analyzed before OCT came into the game?
Well, before OCT, people are looking at the eye with something called a slit lamp microscope, and that project a slit beam, and with high magnification optics, the doctor then look at the eye directly. It could be looking at the front part of the eye, the cornea and anterior chamber, or in the back of the eye, the retina and optic nerve. And often there's additional aids like condensing lens or contact lens that they put on the eye to increase the magnification and aid in stereo perception. The slit lamp use stereo binocular optics, so there's a depth perception. But with OCT, you go from a stereo perception where you can see thickening of the retina on several hundred micrometer scale to being able to detect even small fluid pockets that's a few micrometers. So it's a 10 or 100-fold enhancement of the ability to see in depth. And of course, it's also a digital imaging modality, so you get a permanent record, and the images can be analyzed with computer image processing and artificial intelligence. It's also much gentler for the patient because typically we use infrared light that's not visible to the patient as compared to fundus photography or direct slit lamp examination that use very bright white light that's dazzling and uncomfortable. So it's used pretty much for all eye conditions. So if you go to an ophthalmologist for anything more serious than just needing eyeglasses, you probably will get an OCT scan, both for retinal diseases or glaucoma or disease of the front part of the eye.
So going back to the technical principle of OCT, is it correct then to say that because it's interferometry based, you have a reference arm, I assume, and then because it is incoherent light, you have a very short coherence length, so then you can pick the thickness from which you can obtain your signal. So is it the incoherence that determines the resolution part of this method?
That's right. There is low temporal coherence. But in order to get good signal, you want good transverse spatial coherence. So generally, we use a light source called the superluminescent diode, or for swept source implementation, a laser diode source. These light sources can be focused to a very small spot and can be detected with very high sensitivity. And it's really the development of these light sources plus fiber optics and advanced detectors in the 80s for optical communications that allowed OCT to be developed as a high performance imaging.
That's very interesting because that's actually one of the questions that we typically ask. What would you say are the technologies that already had to be in place for you to be able to invent this? And so now it seems like that actually the boom of telecommunications based on fiber optic cable was important for your discovery. So you're not building something that's free space, but fiber is of substantial importance in your configuration.
That's right. So you don't necessarily need to use fiber optics, but it was really helpful to have simple, robust mode matching between the sample arm and the reference arm by using a fiber interferometer. And of course, fiber optic was developed mainly for optical communications that took off in the 1980s. So high quality fiber optics and fiber optic couplers were available around that time that enable us to build OCT systems. And the lasers, back then was pretty new too. And diode lasers and a variation called superluminescent diode, again, only become widely available in the 1980s.
This is actually something I was going to clarify because you do need coherent light for OCT, right? You need a laser source, not just a light source.
Generally, most OCT systems use a superluminescent diode. So it's actually technically not a laser because it's a more spontaneous emission rather than stimulated emission, but it's confined within a waveguide structure. So it has really good transverse spatial coherence while having a wide spectrum at the same time.
Okay, interesting.
So it's kind of, the light has properties like halfway between laser light and ordinary light. And that is ideal for OCT.
Was it also its coherence, optical coherence tomography, since it was like originally done with the laser, but then later you found out that actually you only need the spatial coherence and maybe not the temporal coherence, or maybe there's like a sweet spot in terms of what is the ideal light source?
Actually, we started out using a superluminescent diode. It's only recently that tunable lasers are being used in a swept source OCT. We started out using superluminescent diodes, which is technically not a laser. There were previous projects in Professor Fujimoto's lab that used femtosecond lasers to probe the time of flight of light reflected from biological specimens. And that did not use interferometric detection. The initial project used nonlinear cross-correlation or second harmonic generation, and that did require femtosecond laser pulses. But that was too difficult, I think, for a routine medical imaging application. And also, actually, the performance was not as good as OCT. So that was just a precursor in stimulating the thought process and project development. And that occurred, I think those projects were ongoing about 5 years before I joined Professor Fujimoto's group in the ultrafast optics group.
So it appears that when you joined, Professor Fujimoto already had the goal of creating instruments for biomedical imaging. What specifically was he interested in, or what did he task you to do when you first arrived as a graduate student?
I had several projects. One was building a picosecond laser system to cut tissue. So it's to amplify a picosecond laser with enough energy to cut tissue. We were thinking that it could be used to cut corneal tissue for refractive surgery or cut the vitreous for vitreoretinal surgery. But I failed in that. I never could get high enough energy to do cutting. So my fallback was to do the second project where my goal was to measure the thickness of tissue layers. Initially, we were thinking of measuring corneal incisions in radiokeratotomy or excimer laser corneal surgery. So it's simply measuring thickness was my initial goal. And we extended that to measuring the retina, measuring retinal thickness. And when we look at the retina, what I realized from the data was that I wasn't only just seeing from the front and back surfaces of the retina, but the instrument has such high sensitivity, 100 dB or 1 in 10 billion sensitivity, that we could actually see internal structures inside the retina. And that's what gave me the idea that this could be turned into an imaging modality because we were seeing internal structures. So we changed the goal of the project from simply measuring thickness to developing the imaging technology.
How would you see it? Was it an interferogram, which was later like Fourier transformed, or was there any temporal analysis involved? So depending on the length of the tissue, there would be like different time stamps for those signals, or if you could explain that part.
So the initial setup was a time domain OCT, or at that time, since we were not scanning, it wasn't even OCT. You could call it optical coherence domain reflectometry. So we have a Michelson interferometer, and with a superluminescent diode light source that provide enough spectral bandwidth to have 10 micrometer depth resolution. And initially, we did not use fiber optics. So it's a free-based system. You have a beam splitter, and we match the length of the reference arm and the sample arm so that they were approximately equal. And then the reference arm length was modulated rapidly with the motor that changed the position of the mirror. And as it scanned back and forth, it generated an interferogram. You would get a signal peak when the distance to a tissue layer is matched by the distance to the reference mirror. When we scan the retina, we'll see signals from the various layers inside the retina.
So you measured the reflectance of different intensities on which layer it happened in the tissue.
Right. Since the reference mirror is scanning back and forth, as you were saying, the depth in the sample will be time-coded. So you plot the signal amplitude versus time, and that provides the axial scan.
Mm-hmm. And you did it with continuous wave laser. It was not pulsed one.
It was not pulse.
Okay.
It was a superluminescent diode.
Okay, yeah, as you mentioned, you started from superluminescent in the ultra-fast optics group, and you stick with it.
We actually have to modify a laser diode to produce superluminescence. So basically, you take a laser diode and you coat the facets to reduce the reflectivity so it doesn't have sufficient gain to laze, but produces wide bandwidth light on a continuous basis.
Why is it better to use wide bandwidth light? What's the benefit of having multiple wavelengths?
That reduces the coherence length and your spatial resolution in depth. Your axial resolution is inversely proportional to the spectral width. That's how OCT works.